We talked about this kind of problem before. It only made sense while we were studying derivatives to talk a little bit about the antiderivative at the same time. If f prime of x is 3 over x minus sine of x, what was f of x? That's hyperproblem. So what do you guys think? Anybody think they know the answer? What do you have to do this problem? You have to think backwards, right? Which is huge in math. Math is all about, okay, let's do it this way. Oh, guess what? Now we do it this way. Factoring is a huge place where shifting gears is difficult. So, go backwards. So now I've got to do exactly that. Where would 3 over x, where would that have come from? Uh-oh. Nope.
Natural log.
Yes. So really what you're asking yourself is, the derivative of what would be 3 over x, just for that one piece. So if you know derivatives, you should be able to think backwards about them. Where would this have come from? What would the function have been whose derivative is this? 3 ln x. Now the interesting thing about, tell me real quick, I think I've said something about this before, I can't remember now. What can x be here? What's the only thing x cannot be here? There's a little something about natural log that's kind of weird. 0. It could be anything else, right? Up here. The only thing it can't be is 0. I can divide by any other kind of number I want to. I can divide by negative, I can divide by positive. I just can't divide by 0. Are you guys with me? Or somebody's still looking at me like I'm crazy. I don't understand. But if I do this, what's true about this? What does x have to be for this to be okay? Anybody remember? You all seem a few of you guys seem to be able to sketch that one thing by hand, and natural log thing by hand. What's a natural log look like? What's a log look like? Any log. Yeah, it goes, whee, right? So there's an asymptote here. We discussed this before, so I have to do this just to make them match. Just to make their domains match. That will become huge every now and again. Most of the time it's not worth mentioning, to be honest, but it just really depends on what the values you want to put in there are. What about this? Where would this have come from? Derivative of what is negative sign? Yeah, positive cosine. And then there's one extra thing here, to be honest. It's always this. This is one way you can remember. This is a plus 0 here. Where would that have come from? Some constant. I love it. So that's why you always put plus c when you're doing an antiderivative. And I'll be a little more specific right now. It's called an indefinite antiderivative. We'll talk about definite stuff later. It's a little ahead of our time, but still, just throw that out there right now. Just be complete. You almost always put a plus c. We'll just say it like that. Well, it'll become very apparent pretty soon when we don't. How are we doing so far? I mean, this is just differentiation. This is just taking derivatives, but thinking backwards. You know a derivative, you should be able to come back to its original function. All right, what about this one? What if f prime is 1/2 x to the 7th plus 3x to the negative 2? I like that. You would, Jeff. I'm going to try to show you a nifty way to think about this that's going to help you. Just to let you know, this idea is a giant chunk of what's going to cover the rest of the semester. What we're doing right now. It's a huge chunk of what's going to cover the rest of the semester. And thankfully, we're going to develop some rules, sort of like the derivative rules we have, that will help us do antiderivatives. Right? But where would, here's how I do this. This is how I do this. No matter what the hell the number is going to be, where would the x to the 7th come from? Something x to the 8th. So I know that. And then I think, okay, if I take the derivative right now, an 8 would come down. What's supposed to be there? A 1/2. Yeah. Yeah? Good. So it's got to be where? 1/16, right? I love it. You see how to think about that? The x piece, you know what the hell it's got to be. The actual little piece that has the x in it, you know what it's got to be. It's just the constant you then step back and make it all work out. Yeah, like it? And then what happens here? This would have come from x to the -1. Yeah, and -1 would come down. It's supposed to be +3, so it's got to be -3. And you can always double check yourself every step you take. That would be negative, positive 3x to the -2. Bam! Yay! You can always do the derivative because that's easier. And of course, plus c. Cover my ass for the fact that there's +0 there. It could have been a number there that died when I took a derivative. Derivative? What did I put in here? Okay. How are we feeling so far? This is beautiful. This is nice. We should know derivatives pretty well, even though some of us can't say the word. Let's see. What about, here's a good one. This is going to test your paying attention to what I said just a minute ago. So here's f prime. Tell me what f was. What the function was. Tell me what. What are you guys doing first? Yes, you better. Otherwise, there's no way to do this at all. You can't attack that the way it is. You can't. Doesn't mean you can't do anything because I can simplify this, right? So you still work with f prime. I haven't figured out. I'm just going to rewrite f prime is. Some of you guys have this problem where you write f and then you simplify it, but you haven't really taken a derivative yet, but you say you did. So you don't put that symbol until you're actually taking a derivative. It's going to throw me off. It's going to throw you off. Everybody's going to have a bad day. So here I'm just still working with this. So that's x to the 1/5 over x to the 2/3 minus 3x over x to the 2/3. So what can I do with that? Yeah, 1/5 minus 2/3 minus 3x1 minus 2/3, right? Subtract the powers. Subtract the powers, that would be 3, 10, -7 15ths. That's a cool place you could use cross multiplication. 3 times 1 is 3, 5 times 2 is 10, 3 minus 10 is -7 over 15. Yay. All right. Minus 3x to the 1/3. You had a whole x, you lost 2/3 of x, so now of course you got 1/3 of x left. Now you can finally do the antiderivative. Is everybody cool with what happened there? You could find LCD and all that shit, but you know, that's exactly what I did, just shortcut. So what must f of x have been? Can somebody figure out what the power must have been? Yeah, 8/15. So when you take derivatives, I don't know if you remember the shortcut I told you was like 1 minus the bottom, the top minus the bottom. When you do antiderivatives, it's the opposite of that. You take -7 plus the bottom. So it must have been 8/15. Now this is where things get a little funky. If I took this guy's derivative, 8/15 would want to be out here, right? Is there an 8/15 here? So then what must be here to kill it when it comes down? 15/8. And then here, that would have come from what? 1 plus 3? 4/3? So there would want to be a 3/4 here. There's a 3 there. There would want to be a 4/3, sorry. There would want to be a 4/3 here. There's a 3 there. Oh shit. Ah, so you got to go the right way. We want something times 4/3 to be 3. So let's do it this way. Watch what you can do. I want you to really see how this would be times the reciprocal of that. So let's put -3 and let's put the reciprocal of this. Does that work out? 15/8 x to the 8/15 minus 9/4. So if you take this guy's rid of, 4/3 would come down, 4s would cancel, 3 goes into 9 3 times. So let's make, and of course, plus C. So let's make our first little rule real quick. Our first anti-differentiation rule is directly related to our first derivative rule, which was the power rule, the easiest one. Right? When I give you polynomials for derivatives, you're like, thank God, it should be. So the antiderivative of x to the n is, it would come from what? What would the power have been? N plus 1. By the way, this only works if n is not because that would have come from natural log. Anybody cool? This so far, it's not done yet, right? That power's got to go up by 1. That's what we've been doing every single time. And this captures what I was just talking about. Is there, if I take this guy's derivative, won't the n plus 1 come down? Is there an n plus 1 here? No. So how do I kill that n plus 1 that wants to come down? I have a little n plus 1 trap waiting for it, right? I don't want an n plus 1. I don't want it. So there must have been a divided by n plus 1 to kill it. And if it's fractions, it ends up being reciprocals that we put, just like we did here, to kill the thing that wants to come down. This idea of, if it ain't there, but the derivative wants it to be there, I better kill it. That's the thought process to figuring out antiderivatives.
Is that negative x squared?
No, I'm sorry. That was me making little arrows.
Oh.
Thank you. So that's what it is. So if f prime is x to the n, then f was x to the n plus 1 divided by n plus 1 plus c. Now, I want you to really understand this plus c business. If I told you I've got a line with a slope of 3, could you graph exactly the line I'm thinking about? No. Could you graph a representation of the line I'm thinking about, like a representative line? Yeah, what is it you're missing? You're missing some information. I know it's got a slope of 3, so it would have to be like 3x, right? I'm just missing the y-intercept. So there's an infinite number of things that have a slope of 3, an infinite number of lines that have a slope of 3. Right? In fact, this would be y prime is 3. Wouldn't y have to be 3x? Plus c, and so that c is like the y-intercept. That c is the piece of information I'm missing. I know where it's going. In this case, it's just going 3 forever. But what, even if it's a function, I know where it's going, I just don't know where it is at any time. Right? It's like, he's going 80 miles an hour. Where? I don't know. But he just knows he's going 80 miles an hour. So I know how fast it's going in what direction, but I don't know where it is. So that's why we put the plus c. How do I figure out what that is? Somebody has to give me more information. Then I can figure out what c was. Maybe. For example, let me see. Do they do this? Do they do this? It almost doesn't matter if they do or not. Oh, it's too far. Blah, 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 blah. Ah, yes, cool. I love it. They do. So they give me some information here. I want to know what the position function is. So first step is just do like we've been doing, and then you use the information to figure out what c is. So try to find the antiderivative of that, and then figure out how to use that information I give you. So where would sine t come from? Yeah, good. Negative cosine t. Because cosine would go to negative sine. Sine and cosine suck when you're trying to take derivatives and then integration. Got to be careful about when the negative shows up. So the derivative of cosine is not sine. It's negative sine. Therefore, there's got to be a negative sine on the cosine. Where would negative cosine come from? Yeah, negative sine. Sine's derivative is cosine, so the negative sign doesn't change. Plus c. But now I can figure out what it is. How do I use that information? Yeah. So s of 0 is supposed to be 0, and s of 0 is negative cosine 0 minus sine 0 plus c. So 0 equals? Yeah, good. Negative 1. Plus c, so therefore c is 1. So the position function was negative cosine t minus sine t plus 1. Shua! For a different, so this is what's called a initial value. Doesn't have to be a time 0, but that's your classic initial value. At time 0, this is what it was. That's your initial condition, your initial value. If you change the initial value, I very well could possibly change what value c has. More than likely. Not necessarily. Especially with periodic functions. But yeah, how we feel so far. I mean, that's compared to some of the stuff we've been doing. Boys and balloons and shit. That's not too bad. All right. Let me just double check, make sure there's nothing else too freaky. They do have, this is difficult. Remember when I gave you a function, you had sketch a graph of f prime on top of it? I'll make you explain it to you. Remember that? So now you're going to give you a graph of f prime, and you're going to have to sketch f on top of it. Yeah, so that's a possibility. it would be a very rough sketch. More than likely, they'll give you a problem where they give you several functions. You have to identify which is which is the f and which is the f prime. Blah, 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 blah. Okay, I think that's nothing else too freaky. Yeah, okay. So 4, 9 is pretty straightforward. I've been sort of getting you ready for it. 5 is where things get nifty. Very much on purpose. 5 starts disconnected from anything we've done. And then a little bit later in 5, we connect it with basically this, the idea of antiderivative. It's not an immediate connection. It has to be made. So we've already talked about antiderivatives. It makes sense to talk about them because we just talked about derivatives, right? So now we're going to start off with talking about this seemingly disconnected topic, the area under a curve. And then we're going to try to connect that with antiderivatives. Okay. Let's go. So, the general idea is to figure out what that area might be. So, I can't remember now. I don't think I showed you this. Did I show you? I might have talked about it really quickly, but there's a way to prove the area of a circle using a rectangle. Did I show you that? Yes? One person's like, it might have been. But this is really neat if you've never seen this. The way we normally do areas is we try to reorganize it into an area we know. So a really simple example is like a trapezoid. What we do is we cut this into 2 triangles. We find the area of each triangle, and then we add the 2 areas together. That's where the trapezoid area formula comes from. Now, if you've never seen that one, you should go back to that teacher. Slap them too. Kick them in the shin also. If you're interested in that one, anybody want to see that one? Or are you guys like, I don't want to even see this shit. You know, you can add more stuff to it. But like the area of this guy is going to be 1/2 its base times its height. The area of this one's going to be 1/2 its base times its height. They both have the same height. And so the area of the whole thing is, when you add them together, 1/2 h times b1 plus b2. And that's less exciting if you forgot what the hell trapezoid area was in the first place. But it's a b-headed triangle, right? It's got 2 bases. So it's still a 1/2 height times base, but it's like it has 2 bases, so they both get to go in there. That's sort of the way I remembered it a long time ago. Now it's just stuck in my head. I don't have to try to remember. I'm going to try to reorganize a circle into a rectangle. It sounds like you're going to pull a rabbit out of a hat, but here's the reason. So I'm going to do this. I'm going to draw. In reality, there would be many, many more triangles, but I didn't even have enough patience to do that. I just barely made it. So I would cut it out to this edge, but not through the edge, so I can kind of pick it up. So I'm going to cut it across the middle, and then to the edge, so I can pick it up and do like this. Is everybody kind of with me? I can pick it up and just open it, like orange, right? So now it's like this. Right? How long is this? That came from this, right? So how long is this? No. That's not the diameter. That's me picking this up, right? That's opening it up. Boom. It's half the circumference. Circumference is 2 pi r, so that would be pi r. Now, if I do the same thing with the bottom, chop, 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 and I put it, now, especially this becomes perfect if I make a lot of triangles, which is actually kind of cool. It's related to what we're going to do with our function. We're going to cut this up into a very familiar shape. If I cut this up into an infinite number of triangles, this comes out perfect. But this is decent for an approximation. How long is this roughly? R. And so what's the area of that rectangle? Pi r squared. Right? I don't know. Has anybody ever seen that before? No, they just say pi r squared. That's what it is. Moving on. It's a bunch of bullshit. So what we're going to do with this situation is we're going to cut this up into the best, easiest shape for area, which is rectangle. You might argue square, but squares are hard to make general. So rectangles can be very skinny but tall. So you have to be able to, the function could be tall as all hell. So rectangles are a little more versatile. Now you could also do trapezoids and so forth. We're going to start with rectangles. I really want this to be understood. So let me give you the idea, and then we'll do a specific example. I'm going to cut this up into n rectangles. N starts off like 4 and 6. Eventually, we're going to let n go to infinity. If we allow n to go to infinity, our resolution becomes perfect, and we get the exact answer. If we're okay with the resolution being a little bit less, then we can use 6 or 8 rectangles, and that's fine. It's a good approximation. And we make it better by doing some different approaches and averaging them to make it a little bit better. So the first question would be, if I want n rectangles, how wide would each rectangle be? So what do you think? How far do I have to go? B minus A. Is that cool? And I'm going to do what with that distance? I'm going to cut it into how many parts? N. So what I just said should naturally go into what function? What I want to cut it up in. What's another way to say that? Divide it. So I can do B minus A divided by N. That's going to equal the width of one of our rectangles. And we're going to use, hopefully not surprisingly, we're going to use this symbol for the width. Because that's the change in the x direction. And eventually I'm going to let that go to 0, or approach 0. Then we get our infinite resolution, and you're like, where do I buy that to you? Your brain would explode. Okay. Is everybody semi-decent with that? So obviously if it was from 1 to 7 and I wanted 3 rectangles, how wide would each rectangle have to be? From 1 to 7, I want 3 rectangles. Yeah, so I want to go 6. I want to do 3 rectangles. I have to be 2 wide. 2, 4, 6. Hey, I made it. I just got to cover that much range. So I'm going to divide to see how many fit in, or how wide each has to be so I can fit 3 in. The next question really is, all right, so let's say I go out delta x. So this is a plus delta x. Is that cool? That kind of idea is familiar to us. You can add h, that kind of idea. So a plus delta x, I go out that far. How tall is that rectangle going to be? What's going to determine the height of that rectangle? Because if I go up from here, is there a definite height up here? And it's all, here's a can't, it's all. So there's several different ways. Not the change in f of x. I kind of see where you're going, but it's going to make it a little too complicated for like a first basic approach. I mean, you can get really freaking complicated, and then part of you goes, what's the point of this now? I want something simple so that you can do it quickly. So you could do two main different ways. Is either I can use this height, what f of a is, or I can use what f of a plus delta x is. We can use either one of those, but then for every rectangle I would do the same thing. So we call this one, we call left endpoint, because it's the left option. And this one we call right endpoint, because it would be the right option. You guys? So how tall can it be? You could either be all the way up to the right endpoint's height, or it could go up to the left endpoint's height. So they're going to ask you to do this using left endpoints. And then they say, another one's going to say, do this one using right endpoints. So it's really just which side, which thing determines how tall it is. So the way I've drawn it right now is left endpoints. How tall is this first rectangle? How tall is this? F of A. Beautiful. That's how tall it is, right? How tall is it? F of A. If f of a is 7, it's 7 tall, right? If I would have used right endpoint, it would have been f of a plus delta x. That's how tall it would be. I'm going to do that over and over and over again. I'm going to do that here. It's going to be, how tall is it going to be? It's that tall. Here, that's going to be this tall. Here, that's going to be this tall. The next one's going to be this tall, so forth. Do you see how it's over and undershooting in some cases? So if you do both left endpoint and right endpoint, and then average those two, that's what I was talking about earlier, then you get a better estimate than either one. There is one other option, one other main option I haven't talked about yet, and that is not using the left or the right endpoint, but using the midpoint. You can use the midpoint to see how tall it is. Now, I really want to show you why none of this matters in the ultimate goal, which is infinite resolution, making infinite rectangles. Why did none of these matter? Because if I let the delta x go to 0, it gives a shit which point I pick in the middle. They're all going to become 1, right? It doesn't matter then which side I use or whatever. But to make an estimate better for this low resolution problem, like N6 or something, I want to pick one or the other and maybe do some averaging to get a better estimate. All right, let's do a concrete example. I don't want to spend too much time on abstract shit. Let's talk about something concrete. Please, your God, Jeff. So let's do yeah, I like that idea. Let's do yeah. So here's my function, 1 over x. 1, 2, 3. So at like 1, it's 1. At like 1/2, it's 2. For example, just to give a little bit of backstory to it. At 2, it's 1/2. At 3, it's 1/3. So really, this is the area we're talking about. Holy shit. So it's not, it's curved on the top, so that kind of sucks. I made that so big. So first off, we can calculate how wide our rectangles have to be first. Using that, right? So how wide will our rectangles have to be? Yes, 3 minus 1 divided by 4, so 1/2. They have to be half a tick big, right? How we doing so far? And let's say using 4 rectangles, and let's do left endpoints first. So I'd have to say in the instructions which approach to use. I picked this function for a reason, because it's really clear which one's an overshoot, which one's an undershoot. Right? What do I mean by that? I don't know yet. So let's kind of, so here's our A. So A is 1. And let's be a little more specific. Well, let's see. We're using left endpoint. So this will be x1 will be 1. Left endpoints means the first rectangle will be that tall. As tall as it is at 1. That's the left endpoint. Is that decent? When I draw this first rectangle, it's going to go, what's it going to be between? The first rectangle is going to be from 1 to...
1.5?
Yes, from 1 to 1.5. Right? Because it's half wide. So here's where all my rectangles are going to be between. So this first rectangle is going to be up to that tall. Right, and so forth. So is this going to be too large of an estimate or too small of an estimate? Obviously too large. And we're cool with that. So you end up with 4 rectangles. The big mistake I see people do is they'll disconnect from their picture and they'll just keep going with their work. You'll see in a minute how we can just make this almost you almost don't have to draw a picture. But then you always have, like, somebody always has one more rectangle than they're supposed to have, because they want the 3 to show up somewhere. That 3 ain't going to show up anywhere for me, because it does not determine the height of any rectangle. It's the last right endpoint. It's not going to be involved in this at all. But people get focused on this, like, 3's got to be in there, so then they make 5 rectangles, a whole extra rectangle, and their area is way too big. Like, what the hell happened? All right. So can you just tell me the area of this first rectangle? Yeah, it would be the width times the height. And of course the height, let me be really, really specific here. So the width is 1/2 and the height is f evaluated at the left endpoint of the rectangle. And we can actually just set them all up right. Can we do that? In fact, let me be really, 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 let's just really get to the nuts and bolts of this. It's going to be half f1 plus half f, what will be the next thing? 1.5 plus half f2. So don't they all have a half in it? Right. And I'm just going to keep stepping up by half. You can see this is basically what I'm talking about. You can make the process devoid of any visual, but then there's all these mistakes you can make. F of 1, f of 1.5, f of 2, f of 2.5, and now you got 1, 2, 3, 4 rectangles. You better freaking stop. So it's the width times the height, the width times the height, the width, but they all have the width in them, so I can just factor that width out. That's one of the first little things you can do to make this quicker. All right, now you can fill in all the function values. So f of 1 is 1. What's f of 1.5? This is where I need you to be able to handle it. F of 1.5, 1 over 1.5, 1 over 3/2, so 2/3. Bam! Get away from those suck-ass decimals that are obviously coming out of your calculator. Use your own freaking organic, biologic, whatever the shit calculator. Right? So plus 2/3, whatever, Jeff. F of 2 is 1/2, yeah. All right. And f of 2.5, you can do the same thing. Another way you can do f of 2.5, 1 over 2.5, can't you just double the top and the bottom? To make it a nice whole number on the bottom, so it's 2/5. Now, I mean, I'm not going to make you do all that fractioning, to be honest. Just throw all that shit in your calculator, it's fine. But if you estimate in the middle of a problem, your answer is accumulates all your errors. So don't estimate these. 1/2 is 0.5, you can't go wrong. But, and this is 0.4, you can't. But don't estimate this, because then your answer is going to be off. So So you can plug all this shit in your calculator directly. 1/2 times 1 blah 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 blah. So let's see if we get the same thing. I'll try it out. Didn't bring a calculator. What the hell's wrong with you? It's freaking math class. Shit. What do you guys get? Yeah, there you go. 1 point, blah, blah, blah. 1.283 forever, it looks like. I'm not sure what happened to some of you guys. Let's see if I can figure it out. Only mistake I could think of gives me 2.07. You should get 1.283. I mean, in your calculator, it should look like 0.5 times parentheses 1 plus 2 divided by 3 plus 0.5 plus 2 divided by 5. Right? So make sure you can get that 1.283. Okay. Let me see if you guys can handle this. I want you to realize most of the work is done for this. Do this again with right endpoints. Which means the height of the first rectangle will now be governed by what? 1.5. So you won't have f of 1. You'll have f of 1.5. You'll have f of 2. You have f of 2.5. And you'll have f of 3. Hopefully you guys realize you just replace that with f of 3. That's all the work's there. That's the beautiful thing about doing the right endpoint. Most of your work's done from left endpoint. Do what you can. Talk about it. Is everybody cool with every, you can take a 1/2 out. That's the width times the height. The width times the height. I'm just adding 4 rectangles together. That's all this is. The height just happens to be coming at me from a function value, because the height goes up to the function and stops. So that's why I'm doing the f of 1 is the height at 1. F of 1.5 is the height at 1.5. So there's still rectangles. That's all we're doing is adding rectangle areas. So now that's the purple lines. Those are all going to slightly undershoot. That's why the idea of averaging the left and the right averages out any over and undershooting. Does that make sense, Betsy? Now some functions, if they are symmetric across the interval that I'm interested in will average themselves out. Then it doesn't matter which approach you use, you get the same answer. Because it'll over and undershoot just the same amount. So see what I mean? You've already got these figured out. 2/3 plus 1/2 plus 2/5. Now I just got to do f of 3, which is just 1/3. So you get 1 plus 9/10. 1.9 divided by 2 is 0.95, yeah, thank you. So that's an underestimate. This is area using right endpoints. This is an overestimate. This is area using left endpoints. So if you average the two, it's still an estimate. It's not right, but it's a much better estimate than either one of these two. So what do you get when you average the two together? Six one six six one. Oh.
0.95 and 1.33.
I'm trying to figure it out in my head. What is it? 1.1125. 1.65. Okay, that's the part I was trying to think about in my head. Cool. So, and if you use midpoints, very often it'll be close to this already, because midpoints sort of average them out in the middle of the whole problem. So midpoint seems like a really good idea. To be completely honest, you could use random points in between each. You can totally at random. I want that one now. Now I want that one. Now I want this one. Now I want this one way over there. I mean, it doesn't truly matter, because what we're eventually going to do is let all these widths go to 0 or approach 0, in which case you have no options. Whatever method you want to use, all kind of gets squunched up into, well, you got to do this one thing. Is that, if I let the rectangles go to infinity, you ain't got no options. And the width is going to be basically 0. Width will be dx then. Let's try to capture what we're doing more formally, and then we might take a break if you guys want to. So here's what we're doing. The area under the curve, let's say, is approximated by, see if you guys remember this notation. Please tell me you've seen this notation before. If not, please tell me. It's fine if you haven't. We've got to talk about it then, because it's going to show up. Summation notation? Sigma notation? If you take statistics, you've definitely seen it, but they should have taught you this in like algebra. Definitely pre-calc should have seen some of this. So sum, I equals 1 to n. Little I just means which rectangle I'm talking about. Right? Because I'm going to have n rectangles. So that's why I'm going to add n things. The first rectangle plus the second rectangle all the way to the nth rectangle. They're all going to have a width in them. Let me put that at the end. And the height is going to be f at xi. And that xi, like I said, could be a random point. It could be always the left end point. It could be always the right end. It could be always the midpoint. It could be sometimes one of those things. Right? The larger n gets, the less it matters which one you do and if you average them out. The larger n gets, the better everything gets. Does this make sense? Isn't that what we did here? What did we do? We did the width times the function height, the function evaluated. The width times the function evaluated at that point. Then we move to the next one. So just to make sure nobody out there is just keeping mum because they think everybody else knows this. Can you figure this out for me? So this is saying add I squared up for the values of 1, 2, and 3. That's what this notation means. So this would be 1 squared plus 2 squared plus 3 squared. So it's saying let I equal 1 up to 3. So I equals 1, 2, and 3, and then I'm going to add them. Now I'm going to do you something that I wish my teacher would have done. There is actually a giant pi notation that you very infrequently see. This one means you multiply each. Sigma means you add them, because sigma is Greek letter S. So we said, what are we going to use for sum? Let's make it look all neat and use Greek letter. It's like the Super Bowl using Roman numerals, except for like the 50th was L. I don't think they have a giant L made out of stone drop. You remember that? Super Bowl L. It's like, it's not quite as impressive, guys, as XXVI. This would be 1 squared times 2 squared times 3 squared. Right. We're not gonna do anything with that. I just want you to know it exists. It's kind of nifty. I always thought it'd be easier to remember that sum if I had something to kind of play it off of. So that's times. This is sum because it's the Greek letter S. Sigma, sigma, sigma. Or just sigma. Very often we know it from like fraternities, sororities, whatever. All right. So you guys want to take a break? Or want to do a little more? What's up? Take a break? Let's take a break. Come back at 10 after.